Hi everyone, and you're very welcome to today's Saturday session for Junior Cycle Science, where our topic for today is going to be measurement. Now, throughout today's Saturday session, we're really going to be focusing in on the calculations associated with measurement. So things like distance, time, temperature, speed. We're going to look at acceleration. We're going to look at density. We're going to look at voltage, current, resistance, electrical power. Anything where a calculation is involved in terms of measurement, that's what we're going to be focusing in on today, to make sure if those calculation questions come up, they're usually worth about 6 marks, that we know exactly what we have to do in order to be able to get the full marks for those questions. Now, one of the most important things when we're doing our calculations is the inclusion of units throughout our answers and then for our final answer as well. Okay, so normally what would happen if an exam question came up on measurement, it's generally going to be worth 6 marks. You would normally get 3 marks for substituting into the correct formula, and you would then get another 3 marks for the correct answer. Now, if you were to give your correct answer and you didn't include the correct units, so let's say, for example, you were talking about distance and you didn't include meters or kilometers, you can lose up to 1 or 2 marks because you didn't include the units. So it's really important that we include those. Now, there is this system of units called the SI system, or International System of Units, and that's the modern form of the metric system. So it's the official system of measurement in almost every country in the world. So America being an example of one country that doesn't adopt the same system as us. Now, a couple of the measurements you'll recognise over here already. There we have kilograms, we have the metre, we have the second, this is Kelvin, and so on. And we'll be going through all of those SI units today, as well as other units as well, because it's not just those units that we're going to be working with. We will be working with a variety of units. But just keep this in mind as we're working through each of the different calculations. When you can, include your units. Okay, if they're given in the question, they have to be given in the answer. So the first one we're going to look at today is length. So length refers to how long something is, and there's many different ways that we can measure length. Now, the SI unit is the metre, and the symbol for the metre is just the letter M. Okay, so the first letter of metre, it's the letter M. And we can measure length in a variety of different ways. We could have a metre stick, we could have a measuring tape, and we could have a ruler. Now, if you were ever asked to measure a distance, any one of those could be appropriate, but you're not going to use a ruler if you're trying to measure the length of a classroom. A metre stick would be more important or more appropriate for that one because you're going to get it done more quickly. Okay, so try and pick, if you're ever asked a question, what piece of equipment would you use to measure this length? Is it a longer length? If it is, then you might be more appropriate using a measuring tape or a metre stick. If it's a shorter length, then we might use a ruler. So just depending on the question, just keep in mind which one of those you might use. Now, we could also be asked to measure curve lines, and there's 2 devices we can use for this. One of them is an opposometer, the other is a trundle wheel. And very like the straight lines, one of these is going to be used for short distances, one of them is going to be used for longer distances. Now, you've probably used the trundle wheel more often. That's going to be used for larger distances. So you place it at 0, you run the trundle wheel along the course of whatever you want to measure. This will click every time you reach 1 metre, and then if it goes, let's say, for 5 metres and a little bit, you check where this arrow is going to be. You can see all of the numbers the whole way around. So if it clicks 5 times, that's 5 metres, but then you can check where this arrow ends up, and that will tell you how many centimetres in addition you need to add on. The opposometer is used for shorter distances. So let's say, for example, if you were measuring the length of a road or the length of a river on a map. So you place the point at the starting point of the road or the river, wherever it is. You would run it along the entire course. This wheel is going to move down depending on how far you've moved the opposometer along the road or the river, whatever it is. And then what you do is you actually get a ruler or a metre stick and you run it backwards along the length of that, okay? Because the wheel will actually move back towards where it started. And then if you start, obviously, with the opposometer at 0 on the metre stick and you run it along until it stops, wherever it ends is the total length, okay? So the opposometer is for shorter lines, shorter curved lines. The trundle wheel is for longer curved lines. Mass is another one of the very first things you would have measured when you first came into junior cycle science, and the mass of an object is the amount of matter that's in it. The SI unit of mass is the kilogram, okay, so you might have more often been measuring things in grams in the science lab, but the SI unit, the standard unit, is the kilogram. That doesn't mean you can't measure in grams, because you will, and more often than not you'll be measuring in grams, but the SI unit, the standard unit, is the kilogram. We mentioned there that it can also be measured in grams, And to measure the mass of a solid or a liquid, we generally would use an electronic balance. Okay, so we place a dish on top of that, make sure it's set to 0. You can place whatever substance you want inside it and find out the mass of that particular substance. If you're using a liquid, you might place something like a beaker on top of here, reset it to 0, then place the liquid inside the beaker and you'll be able to find out the mass of that particular liquid. Okay, so the SI unit of mass is the kilogram, also measured in grams, and it's this electronic scales or electronic balance that we use to measure mass. Temperature is just a measure of how hot or cold something is. We generally in the lab would always measure in degrees Celsius, but again, a little bit like the mass, the SI unit is different. So the SI unit for temperature is degrees Kelvin. You're most likely never going to measure things in degrees Kelvin, especially while in secondary school, you're always going to be doing degrees Celsius, but just keep in mind that the SI unit is the Kelvin, and we use a thermometer to measure temperature. Okay, so we can see here roughly the temperature there. This particular substance, whatever it is going to be 55 degrees Celsius, and we can see that because the mercury has travelled up to roughly 55. Okay, really important that if you are finding the temperature of a liquid or whatever it is, that you allow the thermometer a little bit of time to acclimatise when you first put it in. So as soon as you put the thermometer into the liquid, make sure you're not recording, give it a minute or two to settle, and then take the measurement from where the mercury has risen to. A couple of things about temperature as well. Obviously 0 degrees is freezing point, 100 degrees Celsius is boiling point for water, and different substances will freeze or boil at different temperatures, and altitude can have a massive impact on that as well. So if you're really high up in the mountains, the freezing and boiling point of substances can vary. And time, another one of the ones that you're constantly measuring as part of junior cycle science. The SI unit of time is the second. We just use S for seconds. We can also use M for minutes as well. Most likely you would do MIN for minute, and can be measured in hours, days, weeks, months, years, all of that as well. But the SI unit is seconds. And to measure time in the lab, we use a stopwatch. Okay, it could be a physical stopwatch like the one we have over here, but if you're a device school, maybe you have iPads, you can use the stopwatch on that, or even the stopwatch on your phone as well. Okay, so the first calculations we're going to be doing today are the calculations associated with area. And from junior cycle maths, you'd also be coming across this. It's very, very similar. There's actually less calculations associated with junior cycle science area than there is for junior cycle maths. So area is the amount of space that something covers. Okay, so let's say, for example, if you were finding the area of the classroom floor, how much space does the classroom floor actually cover? If you're finding the area of the yard outside, how much space does that yard cover? The SI unit for area is meters squared. Okay, why is it meters squared? Well, if you think of length, the SI unit of length was meters, but if we're finding the area of an enclosed space, it's a 2D object. Okay, that's a two-dimensional object there. So that's why we have a power of 2. It's the number of meters by the number of meters. So two-dimensional, so we have meters squared. Today we'll investigate how to measure the area of a regular shaped object. So something like a square, a rectangle, a circle, a triangle, and also an irregular shaped object as well. So let's say, for example, you wanted to find out the area of your hand, or you wanted to find out the area of a lake on a map that you're investigating. So if you were finding the area of regular shapes, we're going to start off here with squares and rectangles. You might remember from junior cycle maths that the area is equal to the length by the width. Okay, the length of the shape by the width of the shape. And we can see that in the calculation down here. So we have a square, the length is 5 centimeters, the width is 5 centimeters. So we multiply 5 by 5 to get 25, but don't forget your units here as well. It's centimeters and centimeters, so it's centimeters squared. Because of the 2D shape, it's centimeters squared. So entire answer is 25 centimeters squared. Now, how would you get the marks in a question for this? That there would get you your 6 marks because you have the correct answer and the correct units. You normally would get 3 marks for writing down your formula and doing some correct substitution. Okay, so area equals length by width, showing that it's 5 by 5 will pick up 3 marks, and then the extra 3 marks will come from 25 centimeters squared. If you left out the centimeters squared, you would most likely either get 4 or 5 marks. You're not going to get the full marks because you didn't have your units. So we'll see how we get our full marks over here now for this calculation to do with a rectangle. So the area is equal to the length by the width. You can just do letters if you want. The length is 10 meters. The width is 8 meters. Multiply the two of those together to get 80, but to ensure we're going to get full marks, make sure we're writing down meters squared. So the total area of that particular shape is 80 meters squared. A couple more shapes here. So we have triangles. You're probably wondering why this has a half. Why is it always a half that's in this formula? Well, if we quickly look at both of these diagrams down here, a triangle is always a half of a rectangle. So that's the particular rectangle that covers that entire triangle. This one up here is a little bit different. Okay, the reason this formula looks very similar to the one that we had from rectangles and squares is because a triangle is always a half of a rectangle. So that's why that half is there. Okay, so one possible way that you could find out the area of these triangles is just to pretend that the full rectangle is there and then divide your answer by 2 or multiply by a half. You're going to get the exact same answer. So for this particular triangle over here, the formula is a half the base by the perpendicular height. So it's going to be a half by the base by the perpendicular height, so a half by 6 by 8. 6 by 8 is 48, and a half of that is 24. Not forgetting our units there as well, centimeters squared. So for this one over here, it's going to be a half the base by the height, which is going to be a half by 5 by 2. And when we work that out, we'll get 5 centimeters squared. Okay, another way you could have worked that is just to pretend that the full rectangle is there. The area of that rectangle would be 5 by 2, which is 10, and divide by 2 then, which is going to give you 5. And we're getting full marks there. Again, we're guaranteeing that because we're writing down our units as well. Now the final shape we need to know is a circle. And the area of a circle is always found by multiplying pi by the radius squared. Now an approximation for pi is 3.14. Okay, so we can use that, 3.14, or we can just use the pi symbol on our calculator. With questions with circles as well, just be careful because you will normally be asked to round to either 1 or 2 decimal places. So just be mindful for what the question is asking you to do. So down here, the area of this particular circle, we multiply pi, so we're using the pi symbol in this case, by the radius squared. Okay, so by 12 squared or by 12 by 12. So just to make a quick note of that, 12 squared is the same thing as 12 by 12. So we pop all that into our calculator and we get 452.16 centimeters squared. So for this particular question, we were most likely asked to give the 2 decimal places, so that's why it was rounded to that. Now for this one over here, we're actually going to find the area of this circle correct to the nearest whole number. Okay, so we don't want any decimal points in our answer. So the area, the formula, is pi or squared. Pi is 3.14. Now we need the radius and we need to square that. Now we're not actually given the radius in this particular example. We're given the diameter, which is the distance from one side of the circle to the other through the center of the circle. The diameter is always 2 times the radius, or the radius is always a half of this diameter. So if the diameter is 12, the radius is 6. So all you have to do then is pop that into your calculator and we will get 113.04 centimeters squared. Now the question asks us to give it correct to the nearest whole number. So if we look at the decimal points after 113, is it closer to 113 or is it closer to 114? It's closer to 113. So it's 113 centimeters squared. And that's our final answer there for that one. So we've looked at all of the regular shapes up until now. We're now going to focus on how we could find the area of an irregular shape. And one really simple way of doing this is to use grid paper. So let's say, for example, we have a grid that's full of 1 centimeter by 1 centimeter boxes. What that means is that every box on the page is going to be 1 centimeter long and 1 centimeter wide. So to find the area of an irregular shape, you would trace whatever object it is or place the grid paper over whatever object it is, and then you would count the box or tick the box if it is fully contained or more than half covered. So all of these individual boxes in here we can see are fully contained within the outline of the diagram, so that's why they're being included. And these particular ones over here towards the side are being included because they're half or more than half filled. If it's less than half, we're not going to do that, and it will balance itself out. Okay, so it is more of an estimation, but it is somewhat accurate. Okay, so that's for the area of the irregular shapes. Okay, we're now going to look at volume for the next couple of minutes, and very similar to area, we're going to look at how to measure the volume of a regular shaped object and an irregular shaped object. Now, before we move on to that, just one thing to keep in mind: area dealt with 2D shapes. Volume, because we're talking about how much space something takes up, we're going to talk about 3D shapes. So for area, we were talking about units squared when we were calculating our answer. Because it's a 3D shape, it's going to be units cubed or units to the power of 3. So we're going to need 3 dimensions when we're calculating the volume of these particular shapes. So very similar again, we're going to go through the regular shapes, we're going to go through an irregular shape. So for a cube or a cuboid, we need 3 dimensions this time because it's 3D shapes, and the calculation we have for a cube or a cuboid is the length by the width by the height. So for this particular shape over here, the length by the width by the height is going to be 3 centimeters by 4 centimeters by 5 centimeters. Pop 3 by 4 by 5 into your calculator, and we'll end up with 60 centimeters cubed. So don't forget your units there. So units to the power of 3. Over here for the other one, it's going to be length by width by height. So we'd have 4 by 7 by 3, which is going to give us 84 centimeters cubed. So again, just be mindful of the units there. Now for the volume of irregular shapes, it's a little bit different. Okay, if you have a small irregular shape, so let's say for example a small stone. Okay, one way you can do this is to get a graduated cylinder, fill the water level up to a certain amount. So let's say for example 50 milliliters or 50 centimeters cubed. So generally we would write volume as 50 centimeters cubed. That up there will be 75 centimeters cubed. So fill the water level up to 50 centimeters cubed. Really slowly place the small object into the water as well, and then look to where the water level rose to. So if we started off at 50 centimeters cubed over here and it rose to 75 centimeters cubed, you can subtract the smaller number from the bigger number, and the difference, the only difference there is the irregular shaped object. So in this particular case, that small stone is going to be 25 centimeters cubed in volume. If you have a slightly larger one, it's a very similar process. We're going to use this structure or this object called an overflow can. Now, how we would set this up, we would place the overflow can on a box, something similar. Just make sure that the spout of it is higher than the graduated cylinder or the beaker that you're using to measure. You would make sure that the beaker or the graduated cylinder is set up, and you would fill the overflow can before the object is in it. Fill this overflow can with water until it starts to pour out of the spout, okay, because eventually it's going to level off at this level here. So the water level is going to be exactly where the spout starts. Okay, whatever excess water had went into here, just throw away, okay, because this should be completely empty. Then really slowly, maybe tie a string around the object. You're going to place this irregular shaped object into the water extremely slowly to make sure that no excess water was to leave the overflow can. Really slowly place it down to the bottom of the overflow can. The water level is going to rise. Excess water is going to go out through the spout and go into the graduated cylinder or the beaker, which you have over here. Okay, you will then be able to see where the water level rose to, and then by looking at the meniscus, okay, what we mean by the meniscus, I'll just do it down here really quickly. Every time you put a liquid into a container, it'll form a double layer. Okay, difficult to see there. Okay, it'll form a double layer. You have to look at the bottom of the meniscus. Okay, so read from the bottom of the meniscus, and in this particular case, it's going to be 14 centimeters cubed. Okay, so that was the volume of this particular object over here. Okay, so it was an overflow can that we use for the larger objects. Okay, something that we can actually calculate now using the volume which we just calculated and combining it with the mass which we looked at earlier on is the density. Okay, so the density of a substance is its mass per unit volume. Okay, so to calculate the density of an object, we need its mass and we need its volume. Density cannot be measured on its own. Okay, so we need those other two units, mass and volume, in order to be able to calculate density. So the units are grams per centimeter cubed or kilograms per meter cubed. That can change. That's combining the units for mass and that's combining the units for volume. Okay, so that's the mass unit there, that's the volume unit there. Now we can use this triangle here to help us to calculate mass, density and volume. Okay, very like the distance, speed, time triangle. You might have used Dad's silly triangle before. This is very similar. So this is our MDV triangle. So if we want to calculate mass up here at the top, we're going to cover mass, and what we're left with is density times by volume here at the bottom. Okay, so the mass is the density times the volume. We just rub that out really quickly now. If you want to calculate the density, we're going to cover density, and we'll be left with mass divided by, that's what that line there means, divided by volume. And that's exactly what we have over here. Density equals mass divided by volume. And then finally, if we want to calculate the volume, we would cover volume, and what we're left with is mass divided by density, and that's exactly what we have over here. So we can use that MdV triangle to calculate mass, density and volume, but we're going to be focusing in on density now for the next couple of minutes, which is the mass of an object divided by the volume of an object. Now, before we get into that, one thing that always comes up on an exam is whether an object is going to sink or float if it's placed into water. So the density of water is 1 gram per centimetre cubed. Okay, if a substance has a density less than this, so let's say for example 0.95 grams per centimetre cubed, so once it's less it's going to float, but if the density is greater than that of water, so let's say for example 1.1 gram per centimetre cube, then it's going to sink. Okay, so for example a can of Coca-Cola. Okay, so we're going to combine all of that now to try and complete a question here. So a student was asked to measure the density of a block. The dimensions of the block are shown in the diagram. The mass of the block is 128 grams. Calculate the volume of the block. So the volume is the length by the width by the height. Okay, so we're going to fill that in now. So we have 4 by 8 by 2, which is going to give us 64 centimeters cubed. Okay, so that's the volume calculated. Now, if we want to calculate the density of the block, I'm going to do some rough work over here. It's our MdV triangle. We're going to cover density. And we're left that density is equal to the mass over the volume. So let's bring that up here to our box. Density is equal to mass over volume. The mass we were actually given in the question up here, that's 128 grams. The volume was 64 centimeters cubed. So 128 divided by 64 is going to be 2. But don't forget your units. It's 2 grams for every centimeter cubed. Okay, so that will get you full marks there. Now the photo below shows 3 glasses of water labelled A, B and C. An egg was placed in each glass. The photograph was taken when the eggs were stationary, so they were given time to settle. Which glass, A, B or C, contains the egg with the greatest density? So that's going to be C, because it's sunk right to the bottom. The one with the lowest density is going to be A, okay, because it has floated right to the top. So here's another question here. So a pupil measured the volume of a potato using the items of laboratory equipment labelled A and B as shown in the diagram. Name the items labelled A and B. So A, this one with the spout over here, that's our overflow can. And B is our graduated cylinder. Okay, it's not a beaker, it's a graduated cylinder. The potato had mass 175 grams and volume 125 centimeters cubed. Calculate the density of the potato and give the units of density with your answer. So quickly up here, just again, we have our MdV triangle. So density is equal to the mass over the volume. So we write that down over here. Density is equal to the mass over the volume. The mass was 175 grams. The volume was 125 centimeters cubed. And we pop that into our calculator and we'll end up that the density is 1.4 grams per centimetre cube. Okay, and we made sure to include our units of density there as well to ensure that we're getting full marks. Why did the potato sink in water? This comes back to density. So the potato's density, potato had a greater density than water. Okay, so another exam question finished off there on density. Okay, so for the next couple of minutes now, we're going to start to look at distance, speed and time. We've already kind of focused on distance and time already in terms of distance being how far something is or how long something is. So that was associated with length. We measure that in meters, kilometers, whatever that might be. And time we measured in seconds. That was how long something took. Speed is the one that we're really going to be focusing in on now for the next couple of minutes and how we can use all three to calculate each other. So for example, we can use speed and time to calculate distance. We can use distance and time to calculate speed, but we'll see all that in the next couple of minutes. So distance is how far something will travel. Units will be kilometers, meters, centimeters, etc. Speed is how far something travels in a given time. And that makes sense when we look at our units down here. So it's kilometers per hour, meters per second. So for example, if we consistently traveled at a speed of 60 kilometers per hour and we didn't change our speed, in that hour we would travel 60 kilometers. If we were traveling at 200 meters per second consistently, every second that we're moving, we will be traveling 200 meters. So that's what those units mean. And then time is how long it takes for something to happen. So that could be hours, minutes, seconds, whatever that might be. So very similar to the triangle we seen a couple of minutes ago for mass, density and volume, we have a triangle that we can use to calculate distance, speed and time. And how we remember this, the reason we have an old man up here, is Dad's silly triangle. Okay, so Dad's silly triangle, DST for distance, speed and time. So very like the MDV triangle, if you want to calculate distance, cover distance, and we're left with speed multiplied by time. If you want to calculate speed, we will cover speed, and we'd be left with distance divided by time. And if you want to calculate time, we will cover time, and we'd be left with distance divided by speed. Okay, so all of that is going to be important for us now when we start to have a look at some calculations. So just remember DST, Dad's silly triangle. So calculation 1, the graph below represents the journey of a cyclist. Name an instrument that could be used to measure the time taken for the journey. Okay, so you could use a watch, a stopwatch, a clock, whatever that might be. Calculate the average speed of the cyclist. So think of our triangle now, Dad's silly triangle. We want to calculate the speed, so we cover speed, and we're left with distance over time. Okay, so we're going to write that down here. The speed is equal to the distance over the time. The distance travelled, okay, where is it going? So the average speed as he travelled from A to B. Well, as we travelled from A to B, we originally had travelled nothing, but by the time we got to B, we had travelled 100 metres. So that's going to be 100 metres divided by the time taken to go from A to B. So by the time we got to B, we travelled for 40 seconds. And if you divide 100 by 40, we will get 2.5 metres per second. Okay, so full marks there because we filled it into the formula, and we've also included the units as part of our answer. The next one here, the table below shows the distance travelled by two athletes, Orla and Molly, during a 100 metre race. Draw graphs in the grid below showing distance versus time for Orla and Molly. So I'll do it in two different colours. So we're going to look at Orla first of all, which we'll do here in yellow. So after 4 seconds, Orla had travelled 20 metres. Okay, so after 4 seconds, we travelled 20 metres. So that's going to give us this point down here. After 8 seconds, we travelled 40 metres. After 12 seconds was 60 metres. And we can see here, this actually ends up directly proportional. I'll just make a little note of that over there as well. So a perfect straight line. That means directly proportional. So we can join all those points now with a ruler. I won't be able to do that right now, but make sure you do it with a pencil and a ruler. Perfect straight line up to the top. Now we're going to look at Molly. So slightly different. After 4 seconds, we'd done 20 metres as well, which is the same. After 8 seconds was 40, which is the same. But now we have 11.2 seconds to travel 60 metres. So 11.2 is going to be somewhere around here. And then we have to go up as far as 60 metres. So somewhere around there. 14.4 for 80. And 17.6 for 100 metres. So somewhere around there. So if you were to join these now, it's going to change slightly. It's not going to be a perfect straight line, consistently sloped the whole way up. There is changes there. Okay, so it looks slightly different. So that's the two graphs drawn. Calculate Orla's average speed. So again, for speed, that's the distance over the time. What is our distance? What is our time? You actually have loads of different options here. So for Orla, there's a distance and a time you could use. So 20 metres, 4 seconds, 40 metres, 8 seconds, 60 metres, 12 seconds. It doesn't matter which pair you use once you're taking it from the same reading. Okay, so it's 40 metres at 8 seconds, 60 metres, 12 seconds. You can't combine the 40 metres and 12 seconds. Okay, they were different points in time. You have to pick the same ones. So I'm actually just going to pick the middle one there, 60 metres and 12 seconds. So distance was 60 metres, time was 12 seconds, so we get 5 metres per second. And just to show you, it doesn't matter which one you picked. If I picked the last one there, 120, 100 metres divided by 20 seconds, you still get 5 metres per second. You don't have to do the calculation 5 different times, you only have to do it once. It just doesn't matter which one you pick. Okay, so for acceleration now, this is linked to speed. So objects do not always move at a constant speed. Okay, we've seen that in the last graph. One person actually did move at a constant speed because we had a directly proportional line. The other line changed. They speed up and they slow down. And this makes sense. If you were walking, if you were running, there's going to be periods where you might be going faster or going slower. If you were driving, you're going to speed up. Maybe if there's clear road in front of you on a motorway, you're going to slow down if you're going around a corner. So the speeding up of an object is known as acceleration, whereas the slowing down is the deceleration. So acceleration is calculated as follows. It's the change in speed, okay, so the final speed minus the initial speed over the time taken, and the units for acceleration are meters per second, or meters seconds squared, okay, or meters per second to the -2, sometimes it'll be wrote as well. Okay, so any one of those acceptable. So a motorbike accelerates from 12 meters per second to 36 meters per second in 3 seconds. Calculate the acceleration of the bike. So the change in speed over the time is the formula for acceleration. The change in speed, we went from 12 to 36, so that's a change in speed of 24 meters per second. We're dividing that by 3 seconds, and 24 divided by 3 is 8. So it's 8 meters per second, or 8 meters per second squared. Okay, either one of those answers is acceptable. Just make sure we're including our units to ensure that we're getting full marks. The graph shows the speed of a Lewis tram as it travels from stop L to stop Q. Calculate the acceleration between points N and O. So if we look at N and we look at O, at point N, our speed was 10 meters per second. At O, our speed was 15 meters per second. So acceleration is the change in speed over the time taken. So the change in speed when we went from 10 to 15 was 5 meters per second. The time between N and O, so N was 100 seconds, O was 140 seconds, that's 40 seconds. If we put that in our calculator, we get 0.125 meters per second squared. Okay, so 5 divided by 40 is 1/8 or 0.125 meters per second. Okay, so the last set of questions which we're going to focus on today is the electricity calculations, so everything to do with voltage, current, resistance, and electrical power. So we're going to do them in threes. We're going to do 3 calculations on voltage, 3 on current, and 3 on resistance. Then we'll have a look at a couple of questions on electrical power. And then right at the very end, we look at, I suppose, the questions that come up on the final paper associated with everything to do with measurement. So it's usually the question 1 on the final paper. So we look at a couple of examples of those. Now, voltage is interchangeable with the words potential difference. So if you ever see potential difference, voltage is being referred to. A voltmeter is used to measure voltage, and we can see that over here in the diagram because there's a capital V on it for a voltmeter, and the units of voltage is volts. So very similar words there. Voltage measured by a voltmeter, and it's measured in volts. Now, Ohm's law is extremely important for us when we're calculating voltage, current, and resistance, and we can see here we have another triangle which is going to help us with our calculations. So Ohm's law states that voltage is directly proportional to current. And how we use this very important relationship, so very important relationship, VIR, we can use the triangle. So exact same way as the other ones, voltage, if we want to calculate voltage, cover up voltage, it's calculated by the current times the resistance. Just be careful of that because current, we use I for current, it's not C. So current times resistance. If you want to find out the current, we're going to cover up current. It's going to be the voltage divided by the resistance. And if you want to calculate the resistance, we cover up resistance, and it's going to be the voltage divided by the current. Okay, so how we remember this one, that silly triangle was distance, speed, time. VIR is a very important relationship. Okay, so we're going to have a look at a couple of calculations then with voltage. So using the triangle over here, if we cover up voltage, we're left with current times resistance, and that's exactly what we have over here. So what voltage is required to create a 3 amp current in a circuit with a resistance of 3 ohms? So that symbol there is ohms, which we'll come back to in a couple of minutes. So voltage is equal to current by resistance. We'll write down the little formula that's going to help us calculate this. The current was 3 amps, the resistance was 3 ohms, 3 by 3 is 9. Don't forget your volts for voltage is, or your units for voltage is volts, so that's why it's 9V. Calculation 2. What voltage is required to create a 4 amp current in a circuit with a resistance of 5 ohms? So voltage is equal to the current times resistance. You can use the letters if you want, so I and R. So the current in this case was 4 amps. The resistance was 5 ohms. 4 by 5 is 20, and the units for volts is V, okay? So 20 Vs, 20 volts. And the last one here, what voltage is required to create a 2 amp current in a circuit resistance of 5 ohms? So again, the voltage is equal to the current times the resistance. The current is 2 amps, the resistance is 5 ohms, 2 by 5 is 10, and the units are volts. For current then, current is a measure of how much charge is flowing at any point within a circuit. A little bit different here for this one, because a current is measured using an ammeter, and we can see that over here because it has a capital A on this device over here. And the units of current is amperes, or we can shorten that to amps. So again, we can use our triangle now to help calculate current. So to calculate current, we cover current up in the triangle over here, and we're left with the voltage divided by the resistance. So what current is generated when a 9-volt battery is connected to a circuit which has a resistance of 360 ohms? So to calculate current, it's the voltage divided by the resistance. So voltage was 9, and resistance was 360 ohms. And if you divide 9 by 360 on your calculator, you get 0.025, and not forgetting your units there, A for amps. So this one here, a little bit different because it's given in diagram form. Calculate the current in the following circuit. So first thing we're going to do is write down our formula. So current is equal to the voltage divided by the resistance. The voltage, look for the V, it's 12 volts. The resistance is 6 ohms, and 12 divided by 6 is 2. And don't forget your units there, 2 amps, 2A. And the final one on current, calculate the current in the following circuit. Very similar here again. The current is equal to the voltage over the resistance. Voltage in this case is 18, resistance is 3, so the current there is 6 amps. And the final one of these in the very important relationship is resistance. So the electrical resistance of an object, if something is resisting, it's trying to stop. So the electrical resistance of an object is a measure of its opposition to the flow of electrical current. So it's trying to stop the flow of electrical current. Resistance is measured using an ohmmeter. Sometimes actually to measure all of these, you might in the lab use a multimeter, but just know the proper names as well: voltmeter, ammeter, and ohmmeter. A multimeter measures all of them or many of them. This is what an ohmmeter will look like, and resistance is measured in ohms, and the symbol for ohms is the omega symbol. Okay, so that one there. So we're going to calculate resistance now. To calculate resistance, we're going to cover resistance up in our very important relationship, and we're left with voltage divided by current. So what resistance causes a 0.4 amp current to flow when a 1.5 volt battery is connected to a circuit? Well, first thing we do, we write down how we calculate resistance. From the triangle over here, it's voltage divided by current. We were told the voltage was 1.5 volts. We were told the current was 0.4 amps. Divide 1.5 by 0.4, and you get 3.75, not forgetting our unit for resistance is ohms. Use the omega symbol. So resistance 2, this is very similar to the table we've seen earlier on for distance, speed, and time. Calculate the resistance using the following results. And I'm actually going to do this twice just to show you that it doesn't matter which data values you pick. So the resistance is equal to the voltage divided by the current. Make sure whichever values you take, you're taking the ones that are paired up. You can't take the voltage of 2 and pair that with 14.4 of a current. You have to use the ones that are paired up. So the voltage is 2, the current is 3.6. And if we pop that into our calculator, 2 divided by 3.6, we'll end up with 0.56 ohms. Okay, so that was for this particular data set here. I'm going to do it with this one over here as well. So the resistance is equal to the voltage divided by the current, which is going to be 8 volts divided by 14.4 amps. Pop that into your calculator and you will also get 0.56 ohms. You could do it again with this one over here. You could do it with this one here, or you could do it with this one here. Okay, once they're paired off, you're always going to get 0.56 ohms. And very similar for this last one here again, just make sure whichever data values you pick, you're pairing them off. You can't mix and match them. So any of those colors you can pick. I'm actually just going to go with the green one there. So the resistance is equal to the voltage divided by the current. Because we covered resistance over here, we're left with voltage divided by current. The voltage is 3. The resistance is 0.15. Pop that into our calculator and we will get 20 ohms. Okay, so that was voltage, current and resistance. Okay, so the last new calculation we're going to look at today is the calculation of electrical power. Now, if you go into your kitchen or your sitting room and look at any appliance which you might have at home or in the lab, if you look at the back, you will see the power of the appliance, okay? And it's measured in watts. Light bulbs are also measured in this as well. And that's the capital W we can see here, okay? So all of the appliances, you'll see a sticker at the back of them which will tell you this information. So power is measured in watts. And how we calculate power is it's the current times by the voltage. Okay, so we actually use current and voltage to calculate electrical power. When we calculate electrical power, we're actually calculating the rate at which energy is changed from one form to another. So let's say, for example, if you put on your light bulb at home, okay, obviously that's going to give out light. That's what we want it to be able to do. But in order for that to be able to happen, we have to convert electrical energy into light energy. So what energy conversion is actually happening there, okay? Appliances in your household will show you their power. So we've already mentioned power is calculated by multiplying the voltage by the current. Here's a quick example here. So a microwave is connected to a supply of 200 volts. The current is 4 amps. What is the electrical power of the microwave? So power, the formula we have for that is the voltage by the current. The voltage was 200 volts. The current was 4 amps. 200 multiplied by 4 is going to be 800. Don't forget your units there of W for watts, so 800 watts. So this is the question which has actually come up on the junior cycle paper before. So calculate the voltage used for each appliance. So we're actually given the power in this case. So let's just have a quick look here. We know that the power is equal to the voltage multiplied by the current. We actually want to find out what the voltage was. Okay, we know the power and we actually know the current already. So we want voltage on its own. So if we divide both sides by the current, what we will end up with is that voltage over here is equal to the power divided by the current. So I'm just using the letter I there for current, okay? I'll actually write the full words just to make it a little bit clearer for ourselves. So power divided by the current. So I just divided across by the current to work this out. Now, it says to calculate the voltage used for each appliance. Okay, so we have a couple of different calculations to do here. So I'm just going to do one or two of them. You'll be able to do the rest of them yourself anyway. So for the coffee maker, the voltage is going to be equal to the power, which is 1380 divided by 6. So 1380 watts divided by 6 amps. Pop that into our calculator and we will get 230 volts. Okay, if we do it for the television, the volts is equal to the wattage, which is 115. So 115 watts divided by 0.5 amps. Put that in your calculator and again, you will get 230 volts. If you do the same thing here for the kitchen blender and the dishwasher, you will also get 230 volts because that's generally the standard voltage that's supplied to homes. Okay, so that's an example of how to calculate power. We're now going to look at exam questions which have come up based on measurement, and it's very usually the question 1 of papers. So in this one, scientists use instruments such as the ones shown below to take measurements. For each of the physical quantities named in the table below, choose an instrument shown above that is used to measure that physical quantity. Now, it doesn't say that you can only use each one once, but it most likely will end up that way for this particular question. So for volume, we're going to use our graduated cylinder. Volume is used for liquids mostly, well, not just liquids and solids, but we'd use the graduated cylinder for the volume of a liquid. Time, we're going to use the stopwatch, measured in seconds usually. Temperature, we're going to use the thermometer. Resistance is measured in ohms, so we're going to use the ohm meter. And potential difference, also known as voltage, is going to be used or measured by the voltmeter. Okay, so important to know there that potential difference is also known as voltage, and then we can link that up to the voltmeter. And the final question, complete the table below for the instrument shown. In each state what physical quantity the instrument measures, also state the unit used for that measurement. Some parts of the table are already completed for you. So you don't have to use the SI unit, we can actually use any units in this case. Here stick, we're going to measure length, and we can use meters for that. Stopwatch, we're going to measure time, we can use seconds. Graduate cylinder, we're going to use volume. Okay, so we're going to use centimeters cubed or milliliters. Thermometer, we're going to measure temperature. So we can use degrees Celsius. Kelvin is the SI unit, but we can use degrees Celsius in the lab. Newton meter is going to... Now before we finish up today, I'm just going to show you around the ExamRevision website where you can access today's content as well as content for the entire Junior Cycle Science course as well. Now when you log in and make an account, we can see here that for each subject that we have video tutorials, quizzes, presentations, an exam builder and a resource pack. So if we click into video tutorials, today we were looking at physical worlds and we were looking at measurement. So there is full worked out videos there of all the calculations that you need to calculate everything you need to know about measurement. There's also an MCQ quiz which is going to correct itself, so you can click in, answer 15 questions and it will give you a score right at the end, and will also tell you which ones you got correct and which ones you got incorrect, so you can do them again. There's a PowerPoint presentation there so you can pick up some extra notes, and we also have the feature down here to build your exam. So not only are all past state exam questions here, all past mock exam questions are here as well. So you can add whichever ones you want to a mini exam for yourself. Marking schemes are going to be provided as well, so you can complete the exam and correct it yourself, just so you're fully sure you're comfortable with that particular topic. Don't forget as well, we also do have loads of live revision courses happening throughout the year. So these are generally at midterm breaks, the Easter breaks, and in the lead up to the exams in May, June as well. So keep an eye on our website because all details will be announced there. Do link in with our social medias as well, because all details will be given not just of the revision courses, but also of any of the Saturday sessions we have coming up. So thanks a million for coming to today's one on Junior Cycle Science. We'll have lots more subjects coming in the next couple of weeks, and hopefully I'll see you for a science one again soon as well. So thanks for coming.